Hello viewers, welcome to CAE for you. In this video, we will show you the CFD results of a reactive flow analysis performed in OpenFoam. More specifically, it is premixed turbulent combustion of a flame holder. The motivation for this analysis is that for many of the industrial problems like gas turbine engines, it is important to know the aerothermal interactions which governs the combustion stability. To add more complexity, the pressure fluctuations can create acoustic waves which can further interact the combustion process in an unfavorable manner. This creates significant challenge in designing combustion chambers successfully. Lately, lean combustion is gaining importance because of the focus on reduced fuel usage and also the emission. So it is necessary to understand the combustion dynamics with lean mixture. The involved flow field can be complex, which we will shortly see in the CFD results. So understanding the favorable location of the ignition and the timing for the sustained combustion can also be obtained from the simulation. Let us quickly see what we are considering in this analysis. We are considering propane as a fuel with equivalence ratio of 0.65. The equivalence ratio of greater than 1 represents a rich mixture and less than 1 represents a lean mixture. Obviously, we have selected a lean mixture for the above mentioned reasons. Due to computational resource availability, we have to use 2D geometry and the turbulence model used is LES. Of course, it is applicable only for 3D geometry, so this is a kind of a pseudo LES. Surprisingly, the LES model used in this analysis seems to capture the qualitative picture of the combustion process very well. And of course, for the same computational reasons, we will not consider detailed chemistry, so a progress variable is used to capture the combustion process, and the simulation was carried out only for limited time, that is, it has been calculated only for 20 milliseconds. XiFoam solver in OpenFoam supports this kind of analysis, and hence XiFoam will be used for this analysis. Just to have an industrial orientation in terms of carrying out the simulation, though the geometry is simple, it was created using Freecad and the meshing was done using Salome platform and a structured grid was created. CFD tool is of course OpenFoam and the solution is visualized in ParaView. So it follows mostly a industrial approach where you use a CAD program for geometry creation and measures for creating mesh, specific solver to solve the physical equations, and post-processing tool to visualize the results. The CFD model is very simple. We have an inlet and the outlet at the ends. The top, bottom and the flame holder surfaces are modeled as walls. The front and back are kept empty. As we said before, this is a 2D simulation. Let us look into the mesh metrics and convergence details. For this analysis, we have used a very coarse grid of approximately 77,000 cells. However, to keep the CFL number under control, a reasonably fine time step has been used. The run was carried out just for 20 milliseconds in one core, and the machine has only 8 GB RAM. This simulation was run for about 1 hour and 15 minutes. For those who would like to run this simulation, the files are available for a nominal price, which will also help us in bringing better content. The details are available in description. Let us visualize the results. Our primary objective is to look into the thermal distribution. So let us look into the thermal plot. The initial circular patch you see is the ignition patch, which was given for about 5 milliseconds. The charge catches the fire and it starts burning. The evolution of the flame appears to be reasonably captured in the simulation. We could also see the shear layers instability. The combustion zone slowly increases and a larger chunk of the charge starts burning. It is also interesting to see the flow field around the bluff body. So we have superimposed streamlines over the velocity magnitude plot. The recirculation zone behind the flame holder holds the flame. Even keeping a weaker ignition source could initiate the combustion. To understand the ignition dynamics, the time for run may be sufficient, but to know about the further combustion sustainability, the analysis should be run further. However, it is worthy to note that the OpenFoam solver offers promising options in terms of modeling such a complex phenomena involving reactive flow and LES turbulence modeling. Hope you like this video. Thank you for watching and we will see you in the next one.